So what is this gradient of 1 by italic r? Quickly do that. So gradient of 1 by r is minus r cap by r square. So how do you do now? So this one you have to go for your polar coordinate, am I right? Isn't it? What is this gradient? Gradient of a scalar in a polar coordinate, I mean, so in spherical polar coordinate, r cap by 1 dou by dou r of t plus theta cap by r dou by dou theta of t plus phi cap by r sin theta dou by dou phi of t, isn't it? So t depends only on r, that's why only this exists, isn't it? You can write in only one step. What is this one? R cap into dou by dou r of 1 by r, that's equal to r cap by r square with negative sign, isn't it? So similar thing will happen here. You better write italic r as r minus r prime, am I right? I think so. This was there, isn't it? In the previous exercise, he has given this one. How you handle this one? You can't. I think spherical polar coordinate is not a good idea. Or what would you do? Differentiation with respect to r. Remember this derivative. That's with respect to unprimed coordinate. So r we are going to write it as x comma y comma z. R prime we are going to write it as x prime comma y prime comma z prime. Remember, okay? So this derivative is with respect to x, y, z. So now my question is, how do you handle this one? I mean, yeah, you got the answer. How? Using Cartesian? Using Cartesian. Any way of writing that one in terms of spherical? No, isn't it? I mean, this will be vector. Even if you write italic r, how do you write? I mean, magnitude. How do you write this one? Magnitude of r minus r prime vector. Am I right? I think you can't directly write that one. We have to go for Cartesian coordinate. Anyway, so just remember this will be same as this one. Okay? What is that one? Minus italic r cap by italic r square. Okay? Go for Cartesian coordinate and do that one and show that one. Okay? It's needed. Wait a second. So now, so let me complete my argument. If it is del prime of 1 by italic r, what it would be? I'll get my point. Why I have written del prime. So this is now differentiation with respect to x prime, y prime, z prime. This kind of differentiation will come. I mean, gradient or divergence. It will come in the third or fourth chapter. Then there will be one more negative sign. Okay, one negative sign due to derivative. So one more negative sign due to this one. Is that okay? You can do that one again. So take your Cartesian coordinate. Do it like this: x cap that dou by dou x prime of 1 by italic r. Is that okay? So plus y cap by dou by dou y prime of 1 by italic r. So plus z cap like that. Okay, do that one. You will get that one. And write italic r as root of, how did you write? X minus x prime the whole square plus y minus y prime the whole square plus z minus z prime the whole square. Just practice these things. Okay. Yeah. If you take derivative with respect to a primed coordinate, you will get r cap by r square. Okay. This is the most general one, right? This derivative is the most general one. Now let me take again gradient of this one. Gradient of what is the divergence of gradient of 1 by italic r? Gradient of 1 by italic r is a vector. I am going to take divergence. Is that okay? Now that will be, so del dot minus r cap by r square. So minus del dot r cap by r square. What is this one? That is 4 phi delta cube of italic r vector. Is that okay? So somewhere it is needed. Okay, I think in the first chapter, first or second chapter, second chapter. In that there is one problem that you have to explore like that. Okay, so now look at here. You may again, suppose if I ask what is the, so now what is this one, del dot del? You remember that is the Laplacian of that one. Remember, del square of 1 by italic r. Del dot del, we have written that was a second derivative, isn't it? Divergence of gradient. Similarly, del square of 1 by r, that's equal to minus 4 phi delta cube of r vector. That's it. Is that okay? Or start with this one, isn't it? So that was r cap by r square gradient minus r cap by r square. Again take one more so derivative, divergence. So you will get this one. This is the most general one. Wait a second, I want to comment something. Yeah, so now you may tempted to do this one directly in your polar coordinate. What is del square in our polar coordinate? 1 by r square, dou by dou r, 1 by into r square, dou by dou r of 1 by r, del square of 1 by r. Am I right? What would you get now? 0, isn't it? That is wrong. That is wrong. Is that okay? That's why you have to, go with the intermediate step whenever you do that one. Okay? If it is 0, just think over it. Okay? Because del square of 1 by r is nothing but del dot del of 1 by r. Is that okay? Del square of 1 by r is nothing but del dot del of 1 by r. Whenever it is 0, think over it, whether we have done any mistake or not. Okay? So Dirac delta may come into play. Yeah, any question? I think you can try all other problems. If you got any, if you got difficulty, just tell me, let me solve in the evening. Now next one is, so theory of potentials. So theory of, so scalar and vector potentials. Okay, let me just take that one, and that's what I told you to revise yesterday. So theorem 1, or let me take it like this. Suppose now I have curl of some vector field. Okay, I have a vector field whose curl is 0. Okay, I have a special class of vector field whose curl is equal to 0, isn't it? So now look at here. We have seen earlier curl of a gradient of any scalar was 0. Am I right? Do you remember? Curl of a gradient of any scalar, that was 0. So that's why we are going to generalize this one. Whenever that curl is 0, it is like that. So we can write f as gradient of some scalar. F as gradient of some scalar. So he will put one more negative sign. Let me explain later in the practical situation. In the application. Is that okay? Once you write f as minus, so negative gradient of v. So now look at here. So del cross del v. Am I right? Del cross del v. That will be automatically 0. This will be obvious, isn't it? So if any vector field, whose curl vanishes, so then that vector field can be written as gradient of scalar. Is that okay? That should be just, that should be obvious for you. You have to read it again and again so that you should be able to apply quickly. Is that okay? So next one. We shall take this one, theorem 1. So theorem 1. So curl-less field or irrotational field. Curl-less or irrotational. curless or irrotational fields so these conditions are equivalent. So following conditions are equivalent. Following statements are equivalent. Remember, sometimes they will use this word, okay? They will use that word. So for irrotational field, like that, okay? They will use that word. So that's okay, irrotational. Curl equal to 0, you can imagine that irrotational. So divergenceless field have got solenoidal as a one more name. Let me just write down, okay? So that is very strange word, okay? So these statements are equivalent. So first statement. Again, obviously curlless or irrotational field means we say like that because of this fact, am I right? Obviously. Everywhere. So curlless or irrotational field means curl should be equal to 0 everywhere, okay? So next one, as soon as this becomes 0, look at here, we can go for, I think, so don't write this one, our surface integral, open surface integral of del cross f dot dA, am I right? So this we can write it as closed path integral of f bar dot dl bar, am I right? Now look at here, if this is 0 everywhere, whatever the path you take, whatever the closed path you take, that closed path integral is 0, isn't it? If you have any curlless field, its closed path integral will be 0. Okay, can I write second statement? So second statement is, so closed path integral of f dot dl or line integral, we say line integral, closed line integral of f is equal to 0 for any closed loop. Remember, because curl is 0 everywhere, you can take any shaped surface and open surface will always have a boundary, isn't it, as a closed path, and you can use your Stokes theorem to prove this one. Okay, so next one again, so this needs some argument. So whenever closed line integral equal to 0, I mean open line integral will be independent of the path. Is that okay? I mean, so for that I think you may need to refer some mathematics books. So we can write like this, A to B f bar dot dl bar is, what do you mean by A to B? A is one position in space, B is other position in space, position vector, okay, is independent of the path. Or I can, wait a second, let me just argue in a different way. So all are equivalent, okay. So each, I mean one-to-one correspondence here, all are equivalent. Wait a second. So integral A to B f dot dl is independent of the path for given endpoints A and B. Let me tell you why it is like that, because f can be written as gradient. So once you write a gradient of some scalar dot dl, if you integrate from A to B, do you remember it was our first theorem? It was a t at B minus t at A, like that. Is that okay? Those are again equivalent, remember. So now if you state this one first, this is obvious, am I right? If line integral is independent of the path, if it depends only on the endpoint, so then I think we have shown that one earlier, am I right? From this one it is very easy. From this one it requires some more arguments, okay, to go to this one. So whenever curl equal to 0, this will definitely happen, okay. So then what is the next one? Remember, we have to explore this one, we have to explore this property. They may give very lengthy, what you call a line integral. Is that okay? If curl equal to 0, then you don't have to choose their path. Is that okay? So between I mean initial point and end point, you can choose one straight line and you can do that one. Remember, you can explore that one in the problems. So if a line integral is getting too lengthy, check out what is the curl. Okay, if curl is 0, you can explore this fact, isn't it? It is independent of the path. You can take straight line between those 2 points. That would be very simple. So next statement is again that is so same as earlier. F is a gradient of some scalar function. Write down in a sentence. F is a gradient of some scalar function. F should be minus del V. F is a gradient of some scalar function. These sentences are equivalent. Now you can start with any one of the sentences, you can go for other. Is that okay? You can start with any one sentence. You can go for other. So will you start with this one? These are equivalent means that is the meaning. Start with this one. So take curl of gradient equal to 0. Isn't it? So now suppose if you start with this one, so you can show this one. You can use Stokes' law to show this one again. Isn't it? So from this one, show this one, use Stokes' law. So Stokes' theorem is closed path integral f bar dot dl bar, that's equal to surface integral. What is the surface? Surface whose boundary is this one. Any surface whose boundary is this one. So del cross f dot dA. Am I right? So again, if this is 0, this should be 0. Surface area vector, those are real. Am I right? Those are non-zero. So that's why curl should be 0. You can show this one. Or if you start with this one, go for Stokes' theorem, show this one. From, I think these two, so suppose if you start with this one, you can show this one. Why? Look at here, A to B, F dot dl. Am I right? What is F? A to B del V dot dl. What is this one? Any idea? First theorem, fundamental theorem of gradients. Minus V at B minus V at A. Am I right? It depends only on the endpoints. It depends only on the endpoints. Isn't it? This line integral, it depends only on the endpoints. If you start with that one, again you can show this one. Equivalent. From one of the statement, you can go for other statement. Okay? I don't know how you learnt addition and subtraction. So these are as important, as equivalent as addition and subtraction in what you call whole electrodynamics. Okay, these statements, this theorem and this vector calculus. Now theorem 2. Wait a second. Earlier, what did I call that special class of vector field? That was a special class of vector field, whatever the statement we have written for. Now, so in this theorem, again, this is also special class of vector field. So what was the name for earlier one? Curl-less or irrotational. Okay. So now this is divergence-less. Or solenoidal. This word they are using frequently. Solenoidal. Okay, so this word may mislead you. Okay, they may use that one, solenoidal phase. Or divergence-less field means you can quickly get the idea. Is that okay? So now, whenever you have that situation, look at here, divergence-less field. Let me take del dot F is equal to 0. Am I right? Let me take that situation. So now, we have one statement earlier. Do you remember del cross? Del dot del cross A equal to 0. Am I right? Divergence of curl equal to 0, isn't it? That's why. So if del dot F equal to 0, del dot F equal to 0, so that means F should be so some curl of some other vector field. Is that okay? Now these statements are equivalent now. Let me start writing the statement, okay? Divergenceless field means del dot f equal to 0. Okay? Del dot f equal to 0. Now I'll go for my Gauss law, Gauss divergence theorem. Okay, Gauss divergence theorem. So what is that one? Del dot f d tau in some volume, that's equal to closed surface integral of f bar dot dA bar. Am I right? Now look at here. Del dot f d tau is equal to closed. Again, what is the surface? Surface which is a boundary of volume. Boundary of volume should be a closed surface. It will be always closed surface. Is that okay? Surface which bounds this volume, isn't it? Now look at here. So since this part is 0, so that's why this should be 0. Now you can take any volume and this part is always 0. So that's why for any surface, for any closed surface, this is 0. Is that okay? So can I write second statement? From Gauss divergence theorems, what is the second statement? Closed surface integral of for any closed surface, write down. So this is 0 everywhere. So for any closed surface, okay. Now again, so from this one we can show this one, or let me go to last statement and I'll come back. Open surface integral. I'm not putting a circle here. Open surface integral. Can you get? That will be that will be independent of the surface chosen. That depends only on the boundary line of the surface. Just like earlier statement. Earlier statement was line integral. Line integral boundaries are 2 points, isn't it? So if you have an open surface, its boundary will be one complete loop. Are you getting my point? If you take any open surface, its boundary will be one complete loop. Now, write down, it is independent of the surface. Is independent of the surface. Independent of the surface for any given boundary line. Is that okay? So take one closed loop, take any surface whose boundary is this closed loop. So this surface integral is what you call independent of the surface chosen for a given boundary line. Is that okay? So that is in case of divergenceless field. Now look at here. Yeah, I haven't argued how this comes. Am I right? I just stated that one. Actually, mathematically, I think we can show from this statement. Okay, when our closed surface integral is 0, open surface integral is independent of the surface chosen, depends only on the boundary line. We can show that one by some mathematical argument, or I'll go to last statement. What is the last statement? What is the last statement? F can be written as, so curl of some other vector field. Am I right? F can be written as curl of some other vector field. Now look at here. So now I'll go for Stokes theorem. Okay, I'll go for Stokes theorem. What does Stokes theorem say? Yes, speak out. So closed surface integral of, no, that's okay. Closed, no, Stokes theorem relates open surface. Why did you say closed surface? How do I start? F dot dA, isn't it? That's equal to closed line integral of surface integral of vector field is equal to closed line integral of surface integral of curl of a vector field. Am I right? Wait a second. del cross F. No, F is equal to del cross A, right? I thought I can come from that last statement. From this one to this one. Yeah, let me start with this one. F dot dA, that's equal to F, I am going to write it as del cross A, okay, dot dA, that can be written as, so try this one yourself later, okay, that can be written as closed path integral of A bar dot dA bar. Am I right? Now, do you remember very earlier I stated this one? This will be independent of the surface chosen. Surface integral of curl of a vector field is always independent of the surface chosen. Now look at here, that statement. So will be there. So I can start with this one. I can use what you call Stokes theorem to write this one. Now look at here. If you want to relate this path and this surface for any given path, closed path, you can choose any surface. This equality is that okay? So that's why. So what do you mean by that one? It only depends on the boundary. It only depends on that closed path you choose. It is independent of the surface chosen. So that's why this surface integral always independent of the surface chosen. Okay? Or let me, I can write this statement also for any vector field. For any vector field, curl of a vector field or surface integral of a curl of a vector field is independent of the surface chosen. Again, you can use Stokes law to show that one. Okay? So write down all of these statements and think over it. Okay? So from one of the statements, you should be able to go for other. And that's what we do usually. Is that okay? So now, yeah, along with all of these, again, I don't have to write that one. These are inbuilt here. So these are inbuilt here. What is that one? I think I have written earlier. So a gradient of a scalar dot dl A to B is independent of path. Depends only on boundary. Boundary means A and B. Am I right? If you take a path, boundary is A and B. So similarly, surface integral of, so can I write V here? That's better because we have used that scalar potential V. Del cross A dot dA is independent of surface, depends only on boundary. What is the boundary for surface? Open surface? That's a closed loop. Am I right? So take any type of surface. I have taken earlier. Am I right? So I have taken a kind of hemisphere. Then I have taken a kind of randomly cut pot like that. Am I right? So boundary line of the surface will be always a closed loop. Any open surface whose boundary line will be closed loop. It depends only on that boundary line, not on surface. Can you feel the similarity, isn't it? This is in case of line integral whose boundary lines are endpoints. This is in case of surface integral whose boundary lines are one closed loop. Given closed loop, right, like this. Boundary is a closed loop. Now look at here. I'll trace it back. So A to B, df by dx into dx. What was this one? Isn't it? This differentiation that depends only on the endpoints. Am I right? Again, that was one variable. This is in case of three variables. Are you getting the similarity? all of these problems, all of this statement, read it again and again, or try to write down and try to go from one statement to other statement. Okay, so that your Gauss theorem and Stokes theorem will also be practiced here. Is that okay? If you try to go from one statement to other statement, obviously you have to use all of the theorems. So do that one frequently, and this is needed. Okay. So now what is the example now? So where we are applying this whole thing, our electrostatic field. Electrostatic field E, it has a special property. What is that? Curl equal to 0. Is that okay? That's why we are going to write E as some gradient of scalar potential. We call it a scalar potential. Let me explain why we take negative sign. Okay, we don't have to take negative sign. Even mathematics will not instruct us to take negative sign. Mathematics says only write that vector field as gradient of some scalar. We will take one more negative sign. Let me tell you, it is to make potential due to positive charge positive. Okay, let me explain later. It is for our convenience. Again, we have magnetostatic field. Magnetic field, it always have a property. What is that? We say magnetic monopole doesn't exist, isn't it? Magnetic charge doesn't exist. If magnetic charge exists, it would have given divergence. Am I right? When you get divergence, when you have a single source, point source. Are you getting my point? I explained, if you have non-zero in this side, that means it will talk about source. So remember, this is consequence of Coulomb's law. This is consequence of Biot-Savart's law. Very basic. Okay, that's why Coulomb's law and Biot-Savart's law, those are basic input. Rest of them are again mathematical elaboration. Is that okay? So once you show this one, how you write this one? B as, you can write a magnetic field. Even in dynamic case also, this is 0 always. Is that okay? But we have to write electrostatic field, okay? Because we have a Faraday law, which is a dynamic case, where we will have del cross E equal to minus dou B by dou T. Okay? Yeah. So up to, I think, electrodynamics and potentials and fields chapter, we need to play with these things. Remember, again, I am stating in Stokes theorem, once you choose one closed path, what is that? Closed path integral of f bar dot dl bar, that's equal to, so any vector field. Curl of vector field, it is independent of the surface for a given boundary line. Okay, remember that one. Now we better to quickly do one problem on I think I don't know whether you have done that one or not. One problem on spherical symmetry, one problem on cylindrical symmetry. Okay. He has taken one hemispherical region. Okay. Hemispherical region. X cap, Y cap, Z cap. Is that okay? Hemisphere. And he has given one vector field. Vector field is equal to r cos theta, r cap plus r sin theta, theta cap plus r sin theta, cos phi, phi cap. How he has given VR r cap, V theta theta cap, V phi phi cap. Is that okay? So that's why you have to use whatever the formula, divergence, whatever you take, you have to take in that coordinate, okay, in the spherical polar coordinate. Now he asked you to verify the Gauss divergence theorem for this surface and volume. Am I right? Gauss divergence theorem connects volume integral to surface integral, closed surface integral. Now we shall do that one. So again, so first thing is you have to take divergence. Am I right? You have to take divergence. So how do you take divergence? 1 by HR, H theta, H phi. So then dou by dou R of VR, H theta, H phi. Speak out. Dou by dou theta of V theta, HR, H phi. Am I right? So plus dou by dou phi of V phi, HR, H theta. Am I right? So 1 by R square sin theta. It takes some space. Am I right? So quickly do this one. Have you done? Have you done this one? 1 by R square sin theta. So dou by dou R of what is VR? R cos theta. Let me write down that one. Okay, R cos theta. What is H theta, H phi? R square sin theta. Am I right? R square sin theta. R cube sin theta. Okay, first part. So plus dou by dou theta. What is V theta? R sin theta. What is HR, H phi? H phi equal to R sin theta. Am I right? R square sin square theta. So yeah, correct. Dou by dou phi. V phi equal to R sin theta cos phi multiplied with HR is 1, H theta is R square. H theta is R. H phi is HR, H theta. HR, H theta, H phi 1 R sin theta. HR equal to 1. HR equal to 1. H theta is equal to dou by dou phi. That's correct. I'm writing that one. Then let me take it outside later. Second one. Yeah. Dou by dou theta. V theta. V theta is R sin theta. HR, H phi. HR, H phi. H phi equal to R sin theta. R sin theta multiplied with R sin theta. Is that okay? Written directly. Do it in one more step. Do it in one more step. Practice this one. Again, 1 by R square sin theta. Wait a second. Cos theta sin theta will come out. What is this one? R cube derivative 3R square. Isn't it? 3R square. Then here I think R square will come out. 2 sin theta. Check it out. So plus R square sin theta will come out. Cos phi derivative. Isn't it? You can cancel out sin theta. So what is the divergence? Divergence of a vector field, that's equal to, I think you can cancel out R square also. Look at here. Yeah. Okay, 3 plus 2, 5 cos theta minus sin phi. Look at here, very simple expression. Now, to show Gauss divergence theorem, look at here. Volume integral of del dot V d tau, you have to show surface integral of V dot dA. Am I right? So keep on writing those statements, okay? I mean, so later we have to apply. It should be obvious. I mean, it should be common sense for you. So by practicing, this theorem should be common sense. I mean, should become common sense. Okay? Yeah. So now, what is volume? Yeah. Where are you? Here. Where R square? Here. H theta, H phi. Okay, R square, R cube. Okay, R square, one more R from this one. Which one you are talking about? This one or this one? Correct. Now look at here. He asked us to verify Gauss divergence theorem for this region. For this region, I better talk about region, isn't it? Because it connects volume integral and surface integral. Now you have to do that volume integral over this hemisphere. Now how do you take the limit? That's it. To do this one, isn't it? This is a volume integral, that is phi cos theta minus 3 sin phi. What is d tau in spherical polar coordinate? Because we are in the spherical polar coordinate. R square sin theta dr d theta d phi. Now, so how do you take the limits? Minus phi cos theta. Okay, 3, wait a second, sorry. How do you take the limits now? Now look at here. Now again, whatever the volume integral, just follow earlier one. I think day before yesterday, I tried to, in the evening, I tried to explain volume integral, am I right? How do you take volume of this hemisphere? So ordinarily. So first you have to run your R from 0 to, what is the radius here? He has given capital R, isn't it? First you have to run your radial part of the integral from here to here. Okay. So then integrate theta from 0 to pi by 2. Okay. Integrate theta from 0 to pi by 2. Then you will get this plane, area of this plane. Are you getting my point? Then run your phi, so throughout 2 phi, you will get volume. Are you getting my point? If you integrate theta from 0 to what you call pi, if you integrate theta from 0 to pi, what you get? You will get this one. And then if you integrate with respect to pi throughout 360 degree, you will get total sphere. I have to make it as hemisphere. So that's why you have to integrate theta from 0 to pi by 2. Then that will become a plane of this shape. Now again, this is pi, remember. Now run that pi from 0 to 2 pi so that it will just trace one complete circle. It's a kind of rotation of this plane about this axis. About z axis, rotation of this plane, whatever I have marked, okay, about z axis, you will get a complete hemisphere. So that's why, what is the range? R should run from 0 to R, theta should run from 0 to pi by 2. Remember, it should run in your mind. What will happen when you do that one? When you do these two, you will get a surface area of this one. Then you have to run phi from 0 to 2 pi. Then you will get your volume integral answer. Is that okay? Suppose if you wanted to do lower hemisphere, then what will you do? Lower hemisphere. Which one? How do you change that one? R0 to R, am I right? Then minus pi by 2 to? So why can't you take pi by 2 to pi? Isn't it? Pi by 2 to pi. You can take pi by 2 to pi, then again you can run your pi. That's also okay. Okay? Yeah, but he is asking upper hemisphere. Now, wait a second. Now, next part again. So, can you do this one? So, proceed and verify answer with solution manual. Okay? Now, next one. Again, in the exam, we don't need how to prove this theorem, okay, or how to verify this theorem or something. But so these ideas are needed, coordinate geometry ideas are needed, okay. Now I have to do surface integral, that is to close the surface integral, this part, isn't it, over this hemisphere. Closed means, so spherical, I mean your curved part and planar part. So can you imagine that plane is on xy plane, I mean that planar part, that bottom surface, that is on xy plane, is that okay? So now look at here, that closed surface integral, v bar dot dA bar, I have to divide that one into curved one, v bar dot dA bar plus planar one. V bar dot dA bar, check it out. Am I right? I can divide that closed surface into this curved part and into planar part. Is that okay? In that curved part, if you take any patch of area, what is the area vector direction? r cap, am I right? dA vector will be along r cap. So take area vector on the surface. Always it should be outward from that region, isn't it? Are you getting my point? Area vector should be outward from the region and perpendicular to the surface. So in case of this theorem. So that's why, so in that curved part, your dA vector should be r cap, how we have written? H theta, H phi, d theta, d phi. Do you remember? Write down this step and then go for so elaboration. What is that one? R square sin theta, d theta, d phi, r cap. Okay? Yeah, speak up. So now that is for curved surface integral. You got dA vector. You already have a vector. Okay, you already have a vector field. Just take a dot product. Only r cap component will remain. Okay, when you take a dot product. Is it clear? Again, r cap is equal to 1. R cap dot theta cap is equal to 0. R cap dot phi cap equal to 0. Orthogonal coordinate system. Okay, orthogonal coordinate system. That's why. So other dot products are 0. Wait a second. That's okay for curved. You got dA, so then you can do that one. Again, while doing the surface integral, how do you run theta and phi? Now look at here, only theta and phi are variable. Wait a second. You are talking about on the surface, am I right? You are going to do this integral on the surface. You have to write r equal to capital R. Is that okay? And you have to put r equal to capital R in V also. Okay? In the whole step, you have to take r equal to capital R because that's a surface integral that runs over the surface on which your radial distance is constant. Is that okay? So in that one, again, you look at here, your integral is with respect to theta and phi. dr will not come at all. Automatically. Okay, it will take care. Our coordinate geometry will take care. Is that okay? Now, how do you run theta and phi? Same as earlier. Okay, if you run theta from 0 to pi by 2, you will get this arc. How do you find the area? Your surface area of this bowl. So to run theta from 0 to pi by 2, you will get this arc and run that arc throughout 360 degree. You will get a surface. Is that okay? So that's how you have to do. Again, theta is running from 0 to pi by 2. Pi will run from 0 to 2 phi. Is that okay? Because that integral will be d theta d phi. Okay? So that is this part, curved part. Okay? Do this one yourself. Or if you can't do, again, let me explain again, because so you need this much imagination. So planar surface. Again, look at here, your vector field is given in terms of polar coordinate. Okay, even though it is a plane, you can't do that one in a Cartesian coordinate. Is that okay? So even if it is a square, that kind of thing, I think Cartesian coordinate would be better. Again, it's a circle, am I right? It's a disc kind of plane. The shape is a kind of disc, am I right? Again, you have to go for some polar thing only. So now, again, one thing is this vector field is given in polar coordinate. That's why you have to handle that one in polar coordinate. Okay? So now look at here. Now I better to redraw this one. Now you have to do surface integral on xy plane, am I right? Like this. Now, what is the area vector direction? It should be outward from the region. Remember, if you take any area vector here, its direction should be like this. Okay, its direction should be outward from that region. So that was a convention that we have taken in case of closed surface integral. Is that okay? Now look at here. This dA vector, when it is outward from the region, again take xy plane. Y here. Again, your dA vector will be, so like this. Suppose if you take any patch of area, so patch of region, okay, your dA vector is along this direction, am I right? Now, how do you write dA vector? Now, don't go for writing that one as dx dy. Why? Dx dy minus z cap. You can write like this, am I right? Because that variable is x and y in that plane minus z cap. But your vector field is given in polar coordinate. That's why you have to write that area vector in polar coordinate. Now look at here. Take any point in xy plane. Any point on xy plane. Okay. So now what is your radial vector? It is like this. And let me take somewhere here. Okay. So what is your radial vector? So it is along r cap, isn't it? That's the radial vector. That's from the origin. Whatever the point in space you take, now I am taking point on xy plane. Is that okay? Now what is your theta vector? Theta cap. Theta cap. Look at here. Theta should be measured like this. Am I right? That is 90 degree. So now I told you better to make a kind of door here. Am I right? So now theta cap will be perpendicular to this plane. Now, I mean it is in the plane perpendicular to r cap. This is the theta cap. Actually, that's along minus z cap. Am I right? If you compare with your Cartesian coordinate, theta cap will be along minus z cap. Now r cap cross theta cap. This is pi cap. Is that okay? Pi cap is not needed. What we need here? Theta cap. Our area vector is along theta cap. Look at here. Now, in this surface, if you are talking about this area vector which is downward, that area vector is along theta cap. How did you return that one? HR, H phi. Now look at here, r and phi become automatically variable. On that plane, what are the variables? Theta equal to 90 degree. Theta equal to 90 degree on that plane, remember. Whatever the point you take, on that plane, theta equal to 90 degree. So angle from the z axis, isn't it? And only r and phi are variable. Automatically it will happen, okay? Now what is HR? 1 H phi, r sine theta, but you have to put theta equal to 90 degree because you are doing that integration on that plane. Okay, r sine theta, dr d phi, theta cap. Dr d phi, theta cap. Theta is equal to 90 degree or phi dot. You can put sine theta equal to 1. Okay, once you get this one, just substitute that one here. Am I right? Let me write like this. And take dot product with v and do that one. Now, how does r run from? Now, look at here. Dr d phi means r is a variable. R runs from 0 to capital R. Am I right? This whole total radius is capital R. Then phi should run from? Phi should run from 0 to 2 phi. Done. And try to match with your answer. Okay? I mean, do that one and try to match answer from the solution. So, dA, why dA should point downward? Because now you are talking about closed surface area. In that closed surface area, dA vector should be outward from that region, wherever you take. Is that okay? Net flux, whatever you write, V bar dot dA bar. I told in the very beginning. So, while taking net flux through the closed surface, dA vector is always taken outward from the region. And in Gauss law also, so that is the rule. Gauss divergence theorem. So why dA vector we have chosen outward from the region? You can choose inward, am I right? No, why? Again, why can't you choose inward? To make outward flux positive. Okay, if you choose dA vector outward from the region, it will automatically outward flux will be positive, inward flux will be negative. Okay? Yeah. Now, so next problem was again, I think 1.43. 1.43. Again, let me explain like that, okay? Let us not spend much time. Again, we are running out of time here. Let me quickly explain this one. This is purely cylindrical coordinate. You will get each and every point from that cylindrical coordinate system just to do this one properly. So let me explain briefly, okay? You better think over it because again I am running out of time here. I have to explain Gauss law today. quarter of a cylinder. Can you imagine? Quarter of a cylinder. Approximately. Quarter of the cylinder. So where this is 2, this is 2, this is 5. Obviously, you have to write everything in cylindrical coordinate. You have to do everything in cylindrical coordinate. He has given vector field also in cylindrical coordinate. Look at here, V is equal to S into 2 plus sin square phi S cap plus S sin phi cos phi phi cap plus 3Z into Z cap. Look at here, Vs S cap, V5 phi cap, Vz Z cap. He has given like that. Vector field, you can just imagine like that. V S S cap plus V5 phi cap plus Vz Z cap. You can take divergence using that formula, isn't it? Is that okay? What is divergence now? Del dot V is equal to 1 by Hs H phi Hz dou by dou S of Vs H phi Hz. I hope you can do that one. Vs is given, V phi is given, Vz is given. Like that, do that one. Wait a second, let me just explain limits and what are the surface vector like that, okay? I mean, so he told us to verify Gauss divergence theorem, am I right? So now look at here, volume integral of del dot V, that's equal to closed surface integral of V bar dot dA bar, am I right? Volume is this solid volume, whatever here. Again, you have to call it as a region. You have to verify Gauss divergence theorem for this region. Okay, now look at here. Anyway, you can take divergence, okay, in that coordinate system. And what is your dTau? I think I haven't written dTau yesterday in cylindrical coordinate. Hs, H phi, Hz, ds, d phi, dz. All three are variable. What is Hs? Hs equal to 1. Yes, 1. Is that okay? Yes, ds, d phi, dz. That's your volume element in case of cylindrical coordinate. Okay, take those mnemonics. So now look at here, all S phi z are variable while doing this volume integral. Now how do you run those things? How do you run those? Now you better to go for, again you should understand cylindrical coordinate system, x cap, y cap, z cap, am I right? We have written a point in space which can be represented by S phi z, am I right? S phi z. Now you have to take one projection on xy plane, am I right? Am I right? So this was S, perpendicular distance of that point from z axis, that was S, am I right? What was phi? This was phi. What was z? This height was z. Isn't it? Now look at here, to sweep this region, if you take it as a door, you have to rotate the door from xz plane to yz plane, isn't it? That's it. Now how do you run that volume integral now? First thing is you have to run your S from 0 to 2, because this length is 2, remember. This length is 2 here. First you have to run your S from 0 to 2. Okay? You can, I mean that can be done in any order, okay? First you can do S integral, then Z integral, then other integral, okay? If you first do S integral, like this. Then you do Z integral 0 to 5. Then you will get this planar area. That functionality will be there, okay? You are not getting exactly area. If that is a volume, you can write directly, am I right? Function is going to play the role along with that integration, okay? Now if you run 5 from 0 to pi by 2, it's over. Or you can start, so first integrate S from 0 to 2, okay? Then integrate with respect to 5 from 0 to, this is just sliding this one like this. So that will give area of this one. Then integrate about Z axis from 0 to 5. That also okay. Can you imagine that one? So that is the volume integral. Okay. So S from 0 to 2, 5 from, speak out, 0 to pi by 2. So Z from 0 to 5. Okay, Z from 0 to 5. Over. That is closed. That's volume integral. While doing volume integral, only limits does matter because it's a pure scalar integral. Am I right? While when you come here, now it's a surface. You have to take surface bounded by this volume. Surface which bounds this volume. Now you have to take area vector very carefully, isn't it? Now what are the area vectors in a different region now, isn't it? Now this closed surface area, you have to divide it into curved surface area, upper one, lower one, and other two planes here. Is that okay? Let me start with this one. Let me start with curved surface area. What is your area vector? Take any patch of area here. Its direction is along S cap. Can you imagine? What is S cap direction? This was S cap direction. Isn't it? So that's why while doing this curved surface integral of that vector field, dA vector should be along S cap. S cap, H phi, Hz, D phi, dz, S cap. Now look at here. On that curved surface, your S is same, am I right? S equal to 2 only. Along with S equal to 2, then how does your phi run from? Phi and Z are variable. Let me write this one. What is H phi? What is H phi? Yes, D phi, dz S cap. Am I right? But S is not variable when you go over the surface. Am I right? There is a cylindrical surface. S is not variable. S equal to 2. So phi will run from 0 to pi by 2. Z will run from 0 to 5. That will cover this whole surface. That limit. For the next one, that's for this curved part, okay? This closed surface integral, you have to divide it into different parts. Is that okay? So now for this upper surface. What is area vector direction? Z. You have to write that area vector in cylindrical coordinate. Why? You have to take dot product with a vector field which is written in cylindrical coordinate. Isn't it? So that's why dA Z, what is this one? H phi, ds, d phi, Z cap. Again, what is here? What is here? dA Z, what is this along minus Z cap? Hs, H phi, ds, d phi into minus Z cap. Wait a second. So when you write this one, S ds d phi, phi is variable, S is also variable, ds come into play. What is S running from now? 0 to 2. Phi will run from 0 to pi by 2. Am I right? That will sweep that surface. 0 to 2, 0 to pi by 2. Okay, that will sweep that surface. Again, same thing here. So then what is left? the plane which is in xz plane. Okay, the planar surface in xz plane, the planar surface in zy plane. Again, how do you imagine? So take any patch of area. Now this is S vector, S cap. This is z cap. Z cap will never change. Z cap is same as our Cartesian z cap. Cartesian unit vector will never change. Am I right? Now S cap, I think z cap cross S cap. What is that one? What is your phi cap direction? How do you take phi cap direction? Z cap cross S cap, I think you can write as phi cap. It is in cyclic order, isn't it? Z cap cross S cap. So that is in this direction. You have to take minus phi cap, isn't it? You have to take minus phi cap because your area vector should be outward from that region. Am I right? Outward from that region here is, look at here, that is minus y cap. If you have a surface in xz plane, perpendicular to that plane is y cap. Outward means it should be along minus y cap, but you should not write minus y cap. Why? Your vector field is written in terms of coordinate, that coordinate system. Okay, so that's why you have to write this area vector in this surface, in this back surface. dA, that's along phi minus phi cap, hs, hz, ds, dz. Over hs, hz, ds, dz. Wait a second. S will run from 0 to 2. Z will run from, speak out, 0 to 5. That will sweep this surface area. Am I right? Are you getting my point? S will run from 0 to 2. Z will run from 0 to 5. That will sweep that surface area. Is that okay? What is phi over there? Because your vector field may contain some cos phi or sin phi. Isn't it? 0. Am I right? In that plane, phi equal to 0. How did you return phi? Now, if this door is in zx plane, your phi would be 0. Am I right? So phi equal to 0 in that plane. Suppose if vector field introduces any phi variable, just put phi equal to 0. Cos phi or sin phi like that. Okay. So now what is this this surface? This back surface, which is in yz plane. That's along phi cap, I think. Can you imagine? That's along phi cap. Again, I need one more diagram. X cap, y cap, z cap. Now you have a surface like this. Now your area vector should be along minus x cap actually, if you see from a Cartesian view. Okay, but you should write that one in. Let me take area vector like this. What is this one? Again, so let me take, this is my S vector, S cap. This is my Z cap cross S cap, am I right? Phi cap. Yeah, phi cap, in the phi cap direction, I have my area vector. dA vector along plus phi cap direction, S, Hz, ds, dz. S will run from 0 to 2, this is 2, am I right? This is 2, this is phi, this height is phi. That's why Z should run from 0 to 5. S should run from 0 to 2. That will sweep that surface. I'm talking about this back surface. Okay. So try to do these two problems completely so that polar coordinates, I mean cylindrical coordinate and spherical polar coordinate, you will get complete idea. S cross phi, I'm not getting. Now look at here, it is in cyclic order. Okay, look at here. S cap cross phi, you have to take S cap, phi cap, Z cap. Okay, S cap cross phi cap, you should get Z cap. Okay, phi cap cross Z cap, you should get S cap. So similarly, Z cap cross S cap, you should get phi cap, just like X cap, Y cap, Z cap. So again, they should be in cyclic order. We say like that. Is that okay? So if you take cross product between these two, you should get this one. Between these two, you should get this one. Between these two, you should get this one. If you have ulta, you'll get negative sign. Okay? You'll get negative sign. So, or sometimes, look at here, if you need a vector along this direction, you can take S cap cross Z cap. Am I right? S cap cross Z cap is automatically minus pi cap. You can do like that also. Okay, you can do like that. Think about it. In which cross product you need? Yeah, again, so little lengthy. Once you do this one, once you got this imagination, so it's nothing, remember. So practice at least twice these two problems, okay? So then again, you can try problem number 5, 1.56, 1.57, okay? Try them also. I think I need some more theorems here. Let me grab whenever I need, okay? So that almost completes our vector analysis, whatever we need for our theory, okay? So take a break, we shall discuss Gauss theorem.